content serving platform, WebMD runtime. I'm going to go over a previous architecture, the challenges that impeded scalability and availability. I'm also going to talk about the technology choices and why we made them. But I became really frustrated with the architecture of the system. We had a NAS that didn't fail properly. Content wasn't cached, couldn't be served. Web servers had different objects in the cache. So one web server would serve a page, or the other web server wouldn't serve it. Database clustering software failed. We had several DB outages. And the code of the system wasn't tolerant of any glitch in the database or anything else. So being frustrated really led me to take some action. I didn't want to let our main system for serving content to have all these different types of problems, systemic problems. So I got sponsorship from senior management to set up a team, development and operations folks, to address all these problems. So development and operations, we came together, we created a solution. Then we involved QA folks and project management to help when it was time to do the rollout and implementation. So we're going to go over site architecture, some caching, database, and NAS issues, problem constraints, as well as the solution constraints, and a little bit about some of the resource organizational constraints we had to do. First, I want to go over a little bit about WebMD.
Awesome. Hello? Can you guys hear me? Hear me now? All right, sweet. So WebMD has several web properties, webmd.com, MedicineNet, and our UK co-brand, which is webmd.boots.com. Those are our consumer-related websites. Medscape and eMedicine are geared towards doctors, nurses, medical students. We have over 200 applications which run all of our web properties. So think of, we have a lot of different server farms and not as many servers in each farm. So it's not just one application with hundreds of servers in a farm. We have several different farm types, and those applications are all intermixed. That just gives you some context as to some of the architectural challenges that we face. So I was brought onto WebMD Runtime coming off of a successful product launch of a more complicated system. It was a message board-based system, had a back end that was proprietary, had some caching, front-end layer, and various applications which comprise the system. So it was a lot more complicated than WebMD Runtime. So when I was moved to WebMD Runtime, knowing that this architecture was a lot simpler, I thought that this is going to be a piece of cake. There's probably not going to be a lot to fix. I can not coast, but I can really just get in to see what the architecture is and do we really need to fix anything? Boy, was I wrong. So we're going to go over a little bit about how webmd.com works. This is called a friendly URL, webmd.com/allergies. So your user is going to go, types in that in the URL. It's going to go through a Lever 7 switch, hit the WebMD runtime server. The server then asks the database, says, hey, I have this friendly URL. Give me all of the assets, the object IDs, and the locations of where are the assets. An asset's going to be like XML or XSL. So then the database says, OK, here's your location. Now go fetch it. So the content is stored on a NAS device, and WebMD runtime server goes, fetches the content. The NAS device returns it. Then the server processes the XSL and the XML, smushes it together, processes it, returns HTML to the browser. Pretty simple for a content management system, very standard. The publishing system as well as the runtime system are proprietary, built in-house. We're not using any tools. The system itself is about 6 to 7 years old too. So this all works great when you have, so that process is for new pages, new requests, but we do have caching built into the system. There's two types of different caching objects. First is the page object, and the page object is nothing more than a page construct which is stored in memory, and it's stored in memory for 5 minutes. If there aren't any subsequent requests for that page, then it leaves memory. The process then, if that page is then requested, again, then it goes through the previous process. The WebMD runtime server goes through the previous process of asking the database, give me the assets, goes to the NAS, and then recompiles it. So the second caching object are widgets, which are just code snippets within the page itself. And those are cached just at various intervals. The person who wrote the widget, so whether it's an add module or whether it's data that they're getting from the database, let's say it's top news articles or it's a object of 4 related articles, some of those can be fetched from the database, but the caching itself for that object is determined within the publishing system. The runtime system will cache the widgets on the disk or in memory, and that's also configurable. So as I was learning the system, the caching, the request, it goes to the database, then goes to the NAS, then creates HTML, then there's some caching. That all works great for new requests. So we can cache so we have a request, goes through the system, the page object is cached, all the widgets are cached. So how does stuff get updated if it's already in the cache? Including that page object that's in memory. So you have something like the webmd.com homepage, it's always in memory because it's always getting called. So it will never leave memory. So how do we replace that page construct if it's new? On every web server, there's a background thread that will refresh those cached objects on disk or in memory, as well as the page object. The thread uses kind of a FIFO-like, queue-like data structure. I'm not going to call it a queue because it isn't. It's just a FIFO data structure. If the current cache object is expired or in the queue to be refreshed, then the background thread will go to the database, fetch the metadata, then go to the NAS to get the content, or if the content just originates from the database, we'll just fetch it that. But there are some issues with the background thread, and so we had something happen. So the storage guys come to me and said, you know, the CPU on the NAS head's at 90%. I'm like, oh, okay. So do you know where the traffic's originating from? Yes, it's the system that's generating all the contents, the WebMD runtime boxes. So fine, I'll go find out what's going on, and I'm going to get back to you. But first, I just want to find a little bit more about the NAS. So from a capacity standpoint, how can I increase capacity of that NAS? Let's just say, you know, we need to have this feature that the developers just rolled out. So the storage guys say, you know, I could move some shares to another NAS head, but you'll probably have to buy another NAS head for that particular amount. I'm like, okay, so fine, we can segment everything. But what if our traffic increases fourfold? What if we're going to get featured on the White House site, or Yahoo or Google decides to feature some articles? How are we going to handle that traffic? Because we're currently at 90%. Can I buy a bigger NAS head? No, you can't. Sorry, man. Okay. So the NAS itself has a finite capacity. So the next time, so now I'm going to the developers. And I said, why are there so many calls to the NAS? Why, the storage guys came to me and they said, the CPU's at 90%, if we get if we get a spike in traffic, we're not going to be able to handle it. So the developer said, yeah, we pushed out new code last week. The publishers were complaining that their XSL changes weren't getting out to the site fast enough. So we check if the XSL was changed on each request. Okay, so I took a step back, and I'm like, so let me get this straight. On every page request, I had to repeat it because I couldn't believe it. So on every page request, the web process checks the NAS and sees if the XSL was changed. Yes, said the developer. So I said, okay. So within the architecture that I just described, the caching is not really working. It's going to the NAS for every single request, and this is just not scalable. So talked to the developer, and then he agreed to roll back the change. He says, what we'll do is we'll just add the XSL check to the queue-like data structure for the background thread in a periodic interval. So, okay. But at this point, there was certainly a little bit of contention between me, the operations guy, and the developer too. So we agreed, the operations management, development management, and us, the operations guy and the developers, we identified some things that needed to be changed. We have to work together. We have to have a common goal. And that common goal needs to be site availability and performance. So I've got a question for you guys. With the respect to the background thread on the web servers, why would a background thread on the web server that's trying to refresh the content, why would that be not a good idea? You need one on every web server because the cache, each web server's cache is individual. Okay. So the good thing about the background thread is that it does queue the calls to the NAS and the database. So it creates a barrier for content herding problems. So if a publisher just publishes new content on the home page, not all of the web servers will will fetch the content from the DB and the NAS at the same time. It'll only fetch the content when that web server requests it. So the bad thing about that also is that it creates a different problem that the web servers will get the updated, won't get the, not all the web servers will get the updated content at the same time. If we add more servers to the infrastructure, then there's just going to be more calls to the NAS and database. So if we have something like the 90% CPU on the NAS head issue, that would become exacerbated. And the last point, which we just went over, is the web servers don't have the same cache. So this pull method isn't working well, and we'll need to address it. Last point is, the publishing also could take up to an hour. So when a publisher publishes new content to the website, the new content actually has to be refreshed on each web server in order for it to be served. So it could take a while for folks to see the new content. And that's what the developer was trying to fix with that XSL change. So next we're just going to go over a little bit about what happens when there are just NAS issues. So I get the NAS storage guy says, you know what, I have to take the NAS down for an hour. And I'm like, well, you can't. It serves all the content for the site. You can't just take down the NAS. Our system can't handle it. And it's for all of our sites. I said, firmware updates, dude. That's it. Firmware. I'm like, well, how long does it have to be down? Is it really an hour? Well, maybe. Okay. So you're going to have to do this late at night or early in the morning. So they did. We took an outage and wiped the egg off her face. So went to the drawing board and had to figure something else out. Some other issues we had in NAS were failover issues. So in our NAS setup, we have 2 heads and one's a failover. Sometimes the failover doesn't happen. One of the times it was due to a network configuration on the NAS head. It wasn't reading the heartbeat, so that was an issue. So the developers, operations, and us, operations folks, we got together. For all of the XML, the XSL content, images, we still need a place to store stuff. And it has to be robust. We need it to be reliable. It needs to be over some solid protocol that everybody can use. And for the solution, we also have to take in consideration that we have 200 apps to update. Do we want to do that? Is that necessary? Can we avoid it? We can also use the NAS as a backup method. So we don't have to get rid of the NAS. It's just not going to be in the front line for serving the content. So I don't think anyone on the team, including the development, wanted to replace the NAS. We just wanted to make the platform more reliable and available. So development folks had to buy into the solution as well as us operations guys. There wasn't just going to be this drop-in operations Hail Mary fix or some miracle code fix from the development. We had to work together in order to come up with a solution. But we started asking some fundamental questions: do we still need to use SMB or NFS to access the content? If we choose a different access method, then we have 200 apps that will need to be updated. So as part of the scalability team, that's what we called ourselves for the operations development folks, we had to look at different data stores. Scalability, they're a company I think based out of France. They have a product which is a horizontally scaled data store based on the Chord protocol from MIT. There's a paper on it if you'd like to read that. It had scalable storage, but at the time they couldn't support an SMB or an NFS interface. It was a kind of a HTTP S3 type interface for it. We entertained Cassandra a little bit. None of the developers had experience with the Cassandra, and on the operations side, we didn't really have any expertise running it. MongoDB was starting to get into the company. We had a couple of developers that were using it. They liked how easy it was to store and retrieve stuff. Our database team in the operations side was starting to professionalize it within WebMD, but they were a little nervous about running it. Especially, this is our main content platform. Couchbase is memcached based. It has persistent storage, saves it to CouchDB, key value store in memory. So that's what we picked. How many people are familiar with Couchbase? Okay, a few of you. You know it's different than CouchDB, right? Okay. So memcached is already in use at WebMD. Most of our apps already use it. Developers have already used a memcached client. They know and understand the protocol. They know and understand how memcached works. With Couchbase, you can add servers to the Couchbase cluster, and you don't have to reconfigure all of your web servers. With memcached, if you want to add 10 more memcached servers to your pool, you have to reconfigure, add those to your configuration to every single web server. So it can become a configuration management challenge. So it also has support for hundreds of thousands of transactions per second. That's in their marketing materials. We don't really need hundreds of thousands of transactions per second, but it's nice that it can scale like that. All the content stored in memory. There's fast sets gets. So the NAS is still integrated with the solution, and it's still the source of truth for content. So if the NAS goes away, we can still serve content because the Couchbase cluster is up. If the Couchbase cluster just disappears, then the WebMD runtime system will go to the NAS and get the content. The nice thing about Couchbase is that it already builds on existing technology that is already in place at WebMD, which we are using Memcached. So it was kind of a nice natural evolution to start using that product. So next, I get a call from the database folks. So we have to fill over the DB cluster. The primary node is going to be kaput in a few minutes, and it's got to get failover. How many people have had database clusters fail or the failover fail from primary? Okay, pretty much a good portion of you in the room. No DB failover. So WebMD runtime, it works great when the database is available. This is what happens when the database is not available. This is a recent performance test. So right here is when we shut off the database. The green line are the requests, and the purple line are the errors. So with the amount of requests that are going through the system, equates an error. There's an error that just happens. So if the database is not up, the site is just down. So developers and operations of our runtime scalability group, we got together to determine which problems did we want the group to fix, and we had to get management approval to fix them. So the developers said, well, we need the database available because all of the widgets that need data to render content, and it also houses all of the metadata about rendering that page. It's really important that it's available. So how about caching the mapping from the results or the queries and putting them into Couchbase? That's kind of reasonable, right? Yeah, it's reasonable, but then you could have another not scaling issue, but it's just another point of failure or contention, because now the database is your source of truth, and now you're implementing another caching layer for the database. So the developers were like, well, yeah, but can't we just make the database more available? I mean, why can't it just be up all the time? So I asked, well, are you going to be willing to change any code to help make that database more available? Maybe we can have some backup database or a pool or something. And they're like, no, we don't want to change any code. And management said that too. They said, well, all right, Matt, I want you to come up with a drop-in solution to make SQL Server more reliable, more available, and not change a single line of code or anything. It has to be drop-in replacement. Thanks. Appreciate that. That's not going to be tough. It's not as bad as you think. So here's why. Our data workload does not exceed a single piece of server hardware. We have what's called a narrow read workload. So we can have a copy of that database on a database instance on many nodes. And we can have various web servers connect to those various nodes. So that problem became a lot simpler. Also, for the WebMD runtime system, the data is just all read-only. It's only the publishing system that actually writes anything to the data. So the method that I chose to employ this is actually just use load balancing. And load balancing and clustering are different. Clustering's for high availability. Load balancing is a little bit for high availability, but it's really for distributing the requests. So here's the solution. here's this publishing system, it's a black box, and it writes, it'll write to this SQL server, which will be a cluster, so we can have the writes actually be, have some sort of high availability. And then we implemented some peer-to-peer replication to a node here. Here's a load balancer that can do route SQL calls. So the load balancer, some of them are sophisticated enough now that you can split out selects, inserts, updates, and deletes and put them to different servers. I didn't want to go that route. I wanted to make it simple. I wanted to avoid configuring the load balancer to split up the calls. So I just wanted to avoid that problem. So I just said, you know what? All read-only calls are going to go through the load balancer. But if you're going to write anything, and since it was only publishing system, you're just going to use a direct connection to one of the clusters. So this makes the solution really easy to add another instance for read-only calls. So now if I need to scale the web server layer, I can just add more web servers. If I need to scale the database layer, I can just add more instances of this database. And the peer-to-peer replication will take care of that. So we're feeling really good. We've put something in front of the NAS. We can expand our WebMD runtime cluster. We fixed our database problem. So now what we're going to do is we're going to put everything all together. And we're going to go through how the content is pushed through the system. So a while ago, I was talking about the background thread that was pulling the content. Now where it's going to be pushed. So here we go. We've got, there we go. Here's our WebMD web runtime web servers. Here's our Couchbase cluster. Here's a message queuing product. We use ActiveMQ, but you could use Rabbit. Our NAS, here's our publishing system, and here's our database. And this is just the line that says, and then we have got the load balancer here to distribute the calls. So in the publishing system, it's going to write content to the database, the NAS, and also the Couchbase cluster. So the data, the XML and the XSL that's on the NAS, the same stuff is in Couchbase. So it's going to write them to essentially all at the same time. If one of these fails, then the transaction is rolled back. Then the publishing system writes the object IDs to specific queues. There's a delete queue and a fetch queue. The web servers pick off the IDs from the delete queue and then delete their local cache from it. It also takes the IDs from the fetch queue and then goes to Couchbase to fetch the new content that was published. And then it will recompile the page and recompile any of the widgets that need to be compiled as well. So the web server compiles the page, and then it stores those objects back into Couchbase. So the widget cache itself, which is pretty sizable, stores that in Couchbase. So now we've got the XML content, the XSL content, and the widget cache stored in Couchbase. So if we need to add a new server, it's pretty simple to the mix. The new server loads up. It asks Couchbase for all of the widget cache. The page cache is in memory, so and that will just get compiled at runtime. But it'll take all of the widgets that are already in Couchbase. So the advantage to this is now all of the web servers have the same cache, which is a much better advantage. And also, during the publishing system, since this is a push model, the changes kind of go up in seconds rather than 30 minutes, an hour and a half. So was this worth it? We had a team. We went through a lot of failures together. It was a development and operations team to figure out the solution. And we had a goal in order to improve the availability, reliability, and come up with tools within our own problem constraints. So we fixed our database problem by using peer-to-peer replication and load balancing. And the database team was really a huge key in that, without any code changes at all. We addressed the NAS problem by adding the caching layer and reduced the calls to that. So Couchbase was a big win on that. We changed the cache pull model to a push with the content publishing system. And that also reduced all the publishing times from the system itself. So you could get new content out to the site better, faster, cheaper. Some key benefits to this whole project: we can now serve content faster. There's a lot less latency, because instead of fetching from the content from a NAS device, even though the NAS heads do have memory and cache some heavily accessed files, everything now is resident in memory. And when you get the object, there's no looking for it. There aren't any seeks or anything, so there's a lot less latency. And the performance has also increased. So through the system, we were also able to virtualize the web servers. Previously, the web servers were all physical boxes. And that was also partly due to the background thread, because the background thread was churning a bunch of CPU. So we had some really good success with this. And it wasn't just operations. It wasn't development or QA. We had to set up a multidisciplinary team and come up with the solutions and address the problems. And we did that. So it was a group effort from operations, development, QA, and project management to help drive and put this through. We also had to get buy-in from senior management. I mean, it's fine. We can create a group and work on something, but your other work could have more priorities. So senior management really wanted to make this a priority. We came up with some pretty creative solutions within our constraints. So your constraints are going to have problem and solution constraints as well as resources. So we thought that the solutions we came up with were pretty creative and done in a timely manner. The other thing is that we did a phased implementation. So we virtualized the infrastructure first, then we added Couchbase, and then the messaging systems. And that broke down the solution into very deployable chunks. So I know I'm a little short, but I wanted to thank you for attending the talk. I hope you learned things about my experience with implementing technology improvements within an organization. But at this time, I'd like to handle any questions. Yes, sir.
What was the latency in your peer-to-peer with areas, especially on the heavy load?
Good question. So the latency is about 150 milliseconds. It doesn't have to be on the spot, but as you add more peers, the latency does increase because it's just the nature of it. Yes, sir.
How did you address multiple data centers? Is this like peer-to-peer that's within one database?
It's within one data center. We do have some applications that run active-active in both data centers. This is not one of them. And partly for the reason is we use content switching on our load balancer, and there are different farms that write, let's say, user data. If you log on to webmd.com and you look at symptom checker and you save data there, we don't save the data in 2 data centers. And that switch happens locally at the data center. Yep. Yep. But that is something that we're addressing and trying to figure out how do we get our re-architect our write databases so that we can do that multi-master replication. Yes, sir.
You might know this how do you guys do any front-end caching? Is that something you're going to do, or is that something you don't do?
Very good question. So the question is, do we do any front-end caching? The caching is really built into our runtime system, and that was already there. So we had thought about, well, do we put a varnish in front of it, or a Apache traffic server? I think with varnish you can tag certain content, and you can expire that within the publishing system. There would just be so much, they already had that built. So there would just be a lot of rework in order to put varnish or something else in front of it. So that was the reason why we chose not to go that route.
What about, I was thinking more like a service, like an Akamai or something like that, where you say, hey, we're going to delegate this to you, we're going to expect you to do this version, so you can solve a lot of that performance by never generating the requests.
Sure.
In the farm side of the system.
Sure. There's some business challenges that are associated with that. We do front, so we have www.webmd.boots.com. That's actually fronted by Akamai, and we have some challenges with that. The problem is once you get into interactive applications and user data, then you can't really use a service like that. We also have a couple of challenges where we need to have unique IDs when we pass to the ad server, and so that's another thing that we need to address. Good question. Yes, sir.
How do you load balance your database connection?
We use Citrix NetScaler. They have built-in technology to load balance the SQL connections, and it does least connections.
But what load balance method you use? Like run loading or the connection, least connection, or
Least connections.
least connection?
There's also a table in the database you can tell the load balancer to read a specific value from the database, and you can give it a priority, and you can adjust it that way too.
Right. Even the least connection, it might be the different connection. Like one port might be a huge port, and another connection might be just small.
True.
How can you balance it?
True. You can do it. So you can do it based on priority by assigning that type of priority within a value in the database. That's not. A lot of the queries are very similar, so we don't really have that problem. Yes.
About how many concurrent users does your site manage?
Good question. Around 10 or 11 million.
That logged in at any one time?
No, we have 132 million unique visitors per month.
Concurrent sessions at any one time?
Oh, sorry. Concurrent sessions. So we get about around 1,000. Yes, sir.
What did you do within your development team to prevent the guy from promoting code that hash busts your entire site?
Very good question. We changed the process. So part of it was really working together, understand. The developers weren't writing release notes at all, so as the operations team, when because we would just deploy the code, they're like, okay, we have this new build, we're just going to deploy it. So we would deploy it, and we weren't really told about what all the features were. So they missed telling us that feature. It wasn't the release notes, and then until we started seeing these problems. So now developers have to write release notes. Where do they change the code, and then that gets reviewed. Cool. Anything else? Yes, sir.
So you went from a model where you're caching in the app to one where you were caching NAS-based, cache-based.
Yes.
And you also went from physical to virtual machines. Do you find a lot of contention with the network? You know, as you're having to go over the network to get the cache, and you're working on virtual machines.
No. Performance actually has increased because fetching the content off the NAS was really kind of slow. And then also when we added the databases, added the additional database servers, we didn't really have a problem with the SQL that much because all the load, one server could handle all the load. So once all the content was in memory, we still took the network hit because the content, the XML and the XSLs were on the NAS. So you still take the network hit. It's just now that it's in memory, it's actually a lot faster. Yes, sir. No. So Memcached is used by other applications. So we have got over 200 applications, and some of those use Memcached to store objects. So one application we have is Physician Finder. So you can look for a doctor or a hospital or a pharmacy. Now we get that data from another part in our company, and that data, when we get that data, then we cache that into Memcached. We switch that to Couchbase so that it could be persistent. But oh, good question. So the web servers have their own cache, which is based on memory and file, and it's really a proprietary caching system that was developed on top of the .NET caching that .NET already provides you. So the publishers have a choice when they publish the widgets. They have a choice to either save the cached object in memory or on disk or on both. .NET just I think just provides you with a disk cache. So we expanded that by using the proprietary system. But does that answer your question? Okay. Yes, sir.
How persistent are your caches in terms of, say, a data center failure? If the data center went down, would you have a problem bringing the site back up with empty caches, or would your caches survive that kind of powering down the data center situation?
Good question. So the question was, can we survive a data center failure if the data center got powered down? The answer is yes, because Couchbase is persistent, so it writes it to disk. If a node fails, the whole cluster of Couchbase fails, when it will bring up the data that's saved to disk. Now, I also have the data on the NAS device. So if the Couchbase data is wrong or slightly off, I don't care. I don't trust Couchbase enough yet to be that only source. Yes, so Couchbase will take the data that's on disk and load it in memory. Yes, so the caches, the local proprietary caches that are on the web servers, a lot of those are on disk too. So unless those caches get deleted by manual intervention, then it will not need to be rebuilt or refreshed. So we could just power it on and it will just work. Oh, good question. So If the web servers are down, then it's reading off of the queue. It's reading off the message queue, and then when that server comes back up, then it reads the delete objects off of the queue. Correct.
On a similar note, is there an alternate data path, like if your couch cluster becomes unavailable?
Yep. So if the couch cluster becomes unavailable, then the web servers will just fetch the content from the NAS. The NAS is still the source of truth. Sure. It couldn't handle the load when it was under certain conditions, and we can't buy a bigger NAS. But so what we did is we put caching in front of it in order to alleviate those calls. But temporarily, yes, it can handle the load. Thank you, guys. Thank you very much.